Section 5. Unsupervised Learning for Text. In this section, we're going to do a quick recap of unsupervised learning, just as we did for supervised learning in the earlier section. Then we're going to look at an overview of the architecture of the GenSim library. GenSim library has been written in a very specific way to scale well to very large datasets. Next, we will talk briefly about the news dataset from webhose.io that we will be analyzing. This is slightly different from the webhose.io news corpus that we used in the supervised learning section. We will work through a notebook to extract topics from the news corpus, and then we will evaluate the topics that we derive from those topic models. And we're going to do that using techniques that we'll be discussing shortly.
Finding structure in a text corpus. In this video, we're going to briefly refresh unsupervised learning. In particular, we will discuss the latent Dirichlet allocation, or LDA, and latent semantic analysis, or LSI, as two methods for topic modeling. Unsupervised learning is the process of finding structure within data. Topic modeling is an example of unsupervised learning for text data. We can think about unsupervised learning as a way of finding a more concise representation of that data. So if you're familiar with techniques for dimensionality reduction, such as a principal component analysis, this is along those same lines, very closely related. Now, unsupervised learning, we can contrast that to supervised learning if we think about an example of news articles from the previous section. So in the webhose.io corpus, we had the text of each article and the category it belonged to. And that's basically a human label. Someone has decided that belongs in the sports section or the finance section or the politics section. Imagine the situation where we did not have those labels. For some reason we had lost them, or people had just not organized them around those categories. Unsupervised learning is a way of looking inside the data and deciding how to partition it in some way. In other words, it's a bit like an organic technique to discover the sections that the articles should belong to. And in doing so, we're able to compress our representation of that data. So if you think about clustering, we might have a point that sits in a very high dimensional space. So each point is described by, say, 100 or 1000 numbers. If we're able to do a cluster analysis, and we can determine that each point belongs to either cluster 1, 2, or 3, we're then able to just describe each point as belonging to one of those clusters. So the representation that we need for each point, rather than being 1000 numbers, is simply 1, describes the cluster. And then of course we need some information about where the cluster is centered, but we're able to compress that data. And the more structure there is in the data, the more we're able to compress it. I've just put up the definitions that we covered in the last section as a reminder. Corpus is a set of documents, a document is a continuous piece of text, and a token is a cleaned component of a document. And we can define a topic as a distribution over tokens tending to co-occur in the documents of the corpus. So in other words, each topic is a set of tokens that are more likely to be together in the same document. And we determine what that distribution of tokens and which tokens belong in each topic by looking at the overall structure of every single document in the entire corpus. Just to make that a bit more concrete, if we go back to our example of news articles, if we were to pass in to a topic model all of the webhose news articles from the sports section, the technology section, and the world politics section. But we don't know those labels. We're just passing in all of these text documents and that's all. If our topic model performs well, it will hopefully recover 3 topics because we know that there are 3 topics that have been passed in that corpus. And topic 1 might be defined by a higher co-occurrence of the words baseball, team, transfer, and manager. Topic 2 might be mobile, users, quarterly, and adoption. Topic 3 might be words like UN, president, war, and minister. Now notice that we just know these as topic 1, 2, and 3. We don't know that they correspond to the categories that we expect to find. We have to look at what is in each topic to discern what its meaning is. Along with those topics, rather, for each document, we learn that the document has some overlap or some probability of belonging to each topic. So we might say document 1 is 10% topic 1, 70% topic 2, and 20% topic 3. So in other words, it's predominantly topic 2. And if this is a good topic model, we'll have one of those topics being a very high percentage and the others being very low. So we have a high certainty in saying which topic the document belongs to. So the most important thing to remember is that topics should distinguish documents as effectively as possible. So in other words, we would like to have very, very well-defined topics such that each document is very closely aligned with only one of the topics that we eventually derive from our topic model. Just to make this a little bit more concrete, you can think about this in terms of matrices. So on the left, we have the document term matrix, and this tells us how many times each term appears in each document. So that's pretty much a full description of the data, and it has dimension n terms by n documents. And we can break that down into two smaller matrices. One that says for each document what is the distribution over topics, and then some record of what each of those topics means. So for each topic, what is the distribution over terms? So the thing that the topic model learns are these two components, these two matrices. Now it's worth just briefly mentioning at this point the number of topics should be much less than the number of terms, otherwise we're not really compressing the data very much. The number of terms is typically around 100,000, that's taken from the example we're going to look at shortly, and the number of documents can be up to 1 million. So just to get a sense of what the dimensions of these matrices will look like. So this begs the question, how many topics should there be in a corpus of documents? And the answer is, there is no straightforward answer. The number of topics in a topic model is something that we define. So we decide how many topics there should be. Now, as I said, that number should be relatively small compared to the number of terms, and we may have an idea a priori of how many topics there should be, but it's up to us to choose how many topics there should be in a way that best partitions the data. So the first way of doing topic modeling is the latent Dirichlet allocation. This is what's known as a generative method. Basically, the idea is that each document is made up of a mixture of topics, each topic is a mixture of words, and we keep changing these mixtures and sampling from these distributions in order to make documents, and then we compare with the actual documents that we have in our corpus to see how those two mixtures that we've learned, how they perform. And we keep changing those mixtures until we start to create new documents that look a lot like the old ones. We keep sampling and creating new documents that are indistinguishable from the documents in our corpus. Latent semantic analysis is basically a matrix factorization method. You may be familiar with that term. If you're not, don't worry. The term document matrix is decomposed, and we find that each document is a projection in topic space and each topic is a projection in term space.